Hello Year 12 and welcome back after what I hope was a relaxing half term. We're going to spend 1 week looking at the Year 12 material that you revised and studied for the exam just before half term, and after this week we're then going to move on and start looking at Year 13 material for the rest of the last half term. So this is your last week of AS material. The week's going to be split into 2 lessons. This first lesson is going to focus on the paper 1, the mark schema walkthrough, and then the work for you will be to complete the rest of that paper and submit certain questions to Google Classroom for us to have a look at. And then the second lesson of the week will be going through paper 2, the walkthrough of the mark scheme, and then again you'll be asked to complete the rest of paper 2 that you haven't done already and upload that to Google Classroom. So without much ado, let's have a look at this. Question 1, how many ions are present in 306 grams of aluminium oxide? So down here, moles equals mass over mR, which is 3, so we've got 3 moles of aluminium oxide. The number of particles is therefore that times Avogadro's number, 6.02 times 10 to the 23, which is about 1.8 times 10 to the 24. But we are asked for the number of ions, and in each Al2O3 there are 5 ions. So 1.8 times 10 to the 24 times 5 is 9.03 times 10 to the 24. So the answer is D. Sulfide ion, S2-. Sulfur has 16 electrons, so S2- would have 18 electrons, and it would therefore be 1s2, 2s2, 2p6, 3s2, 3p6, 2, 4, 10, 12, 18, and that of course is D. What is meant by the terms isotopes? All you had to do was say that it had the same number of protons but different numbers of neutrons. Okay, so that was the 2 marks there. The element gallium has a relative atomic mass of 69.735 and it only contains 2 isotopes. Sample of gallium contained that isotope with a relative abundance of 63.25%. Calculate the mass number of the other isotope. You must show your working. Well, essentially your equation for relative atomic mass is the percentage of isotope 1 times by the mass of isotope 1 over 100 plus the percentage of isotope 2 times the mass of isotope 2 over 100. Here you're given the relative atomic mass, which is 69.735. You know the percentage of isotope 1, which is 63.25%. And the mass of isotope 1 is 69. You know the percentage of isotope 2 because you're told there's only 2 isotopes, so the other one must be 36.75% times by what you don't know, which I'm just going to call X over 100. Solve that and you get an answer of 71 here. So correct maths, basically for 1 mark, calculation of mass number with suitable working 1, and notice it does say with suitable working. Correct answer with no working gets mark to 0, okay? A solid white water-soluble compound thought to be magnesium bromide. Student carried out tests to confirm the identity of both ions present. Describe how a flame test is carried out. Any mention of platinum or nichrome wire, 1 mark. Dip the wire into clean, fresh, concentrated. This is all optional, but you had to mention hydrochloric acid for the 2nd mark. dip the wire into the solid and place in a roaring blue Bunsen flame for the 3rd mark. And the advice here, allow loop or rod for wire, but ignore inoculating loop. Okay, loads of you still using inoculating loop, don't do that. Allow any mention of HCl AQ, e.g. cleaning it or mixing it or making a paste. Don't worry if they said dilute, you can ignore that, it should be concentrated. Allow on, over, under, near, shown, above, anything that suggests you're putting this into a roaring blue Bunsen flame. Explain the origin of flame test colours. So you have to mention energy or heat coming from the flame, 1 mark. Electrons are promoted to higher energy levels, 1 mark. Electrons return to lower energy levels, 1 mark. Light, and here you didn't have to say in the visible region, that was optional, but light is released. Allow radiation, allow electromagnetic instead of light. Do not award burning, because of course the flame test, you're not burning the thing, you're not oxidizing it, you're just exciting electrons. Give a reason why magnesium does not produce a flame colour. No emission of light in the visible region, but allow that the light is emitted in the UV, which is correct. They said that IR was okay as well, but light emitted in UV. Any reference to frequency or wavelength being too high or too low. But don't award any mention of bright white, okay? That's when we burn the magnesium and we get that bright white flame, but that's not a flame test, so don't confuse those. Why is the lack of a flame colour not a positive test? Other ions don't produce a flame colour, for example beryllium, which is the one that many of you got. Give the formula of a reagent that will produce a cream coloured precipitate when added to an aqueous solution of magnesium bromide. This is GCSE. AgNO3, ignore silver nitrate. So if you wrote it, I'm sorry, it's wrong. The formula AgNO3, and you did that for GCSE. The identity of the anion may be confirmed by testing the solubility of the cream coloured precipitate in ammonia solution. What would confirm the identity of the anion? Well, it would not dissolve in dilute, so it would be insoluble in dilute ammonia, but it would be soluble in concentrated ammonia, so therefore B. Right, we've got a reaction of magnesium with dilute hydrochloric acid. Write an equation for the reaction of magnesium with hydrochloric acid. Include state symbols. So magnesium solid plus HCl aqueous. Okay, the only time we ever say concentrated for an acid is when we really are using that when liquid is when we're using that super concentrated sulfuric acid for the group 7 redox equations. That's forming MgCl2 aqueous. Again, you need to know that chlorides are soluble with very few exceptions. You need to be able to work out MgCl2, and you also need to know that this is going to release hydrogen gas, and balancing that, 2 of those. Okay, so balance the equation with correct species, 1 mark. All states correct, 1 mark. Don't award for example MgCl instead, or H for H2. They allowed you to give the ionic equation. You could have 1 mark if all the species were correct. Fair few people still unable to calculate the uncertainty. Well, you're told that you'll measure it using a measuring cylinder. There is only 1 measurement in a measuring cylinder, and that is the line. You're told the uncertainty is 0.5 centimeters cubed. You're told that the total volume you're measuring is 10 centimeters cubed. So the uncertainty is the 0.5 over 10 times by 100%, which equals 5. Most people getting that right, but a fair few not. Determine which reagent is in excess by calculating the number of moles of magnesium in hydrochloric acid. 3 marks. I think out of all those I marked, there were only 2 or 3 people who got all 3 marks. Everyone, or most people, were fine calculating the moles of magnesium and the moles of hydrochloric acid, but they either weren't clear for the 2-to-1 ratio, or in most cases they got it the wrong way round. So, moles of magnesium here, 1 mark. Mass, 0.12 grams. The formula mass or atomic mass, 24, so that's 0.005 moles. Hydrochloric acid, moles is concentration times volume, so 0.2 times 10 over 1,000 gives you 0.002 moles. And many people just compared those and then said, well, you got more magnesium. But what you needed to do was you needed to say, because of the equation Mg solid plus 2 HCl aqueous, 0.002 moles of HCl only requires 0.001 moles of magnesium. So magnesium 5 times excess. Okay, lots of people were doubling it, saying, magnesium is in excess because 0.05 is more than 0.002. But no, you needed to specifically show this, that number of moles of hydrochloric acid only requires that number of moles of magnesium, and you've got far more than enough. So magnesium is in excess. What's really interesting is even for those people who worked out magnesium was in excess or stated that magnesium was in excess, they then went and used the moles of magnesium to calculate the next bit, which is calculate the number of moles of gas that could be produced. Well, again, you've got magnesium solid plus 2 HCl aqueous forming MgCl2 aqueous plus H2 gas. 2 of those forms 1 of those. This is a limiting reagent, 0.002, therefore gives 0.001 moles of that. You could have transmission error if you halved your previous answer, but actually I don't think anyone got that. PV equals nRT question. Rearrange the ideal gas equation. V equals nRT over P. There are some people who still don't do the rearrangement, and they just substitute things in and then they rearrange it. So it does say allow mark 1 if equation rearrangement not explicit but used correctly. So if you put the numbers in the right place, you could have it. But it's always worth just writing a rearranged equation. Correctly converting degrees C to Kelvin, I think virtually everyone got that right, 296 Kelvin. Calculating a volume in meters cubed, that was just plugging in everything to get 2.51 times 10 to the minus 5 meter cubed. But then the 4th mark was for converting that to centimeters cubed, and there are still many people that do not know there are 1,000 centimeters cubed in 1 meter cubed. Okay, so you had to times by 1 million to get 25 or 25.1 centimeter cubed. Some people actually not giving their final answers 2 or 3 significant figures and losing a mark because although they'd done all the calculations correctly, they didn't round the final number on the calculator. So you're only allowed for 4 marks 25 or 25.1. And here are some common values if you made mistakes. Deduce 2 possible reasons why the volume of gas collected in the experiment was smaller than that calculated in B4. Right. Now, I did feel for some of you who came up with valid points that could be made, but you know this experiment. You did this basically as one of your CPACs, and I'm sure we have highlighted to you before what they are expecting you to say. So Do not award generic gas leakages from the apparatus. Do not award gas may dissolve in water. Okay, hydrogen does not dissolve, okay? So while that's absolutely fine for carbon dioxide, hydrogen does not dissolve in water. Ignore generic references to the reaction being impure and ignore references to an incomplete reaction. So lots of you mentioning those, and they're not wrong, but they're not what they wanted. They wanted you to say that the gas was lost before the bung was replaced. They wanted you to say that the magnesium was coated with oxide, so water was formed instead of hydrogen. Okay, and that's because we have talked about this situation where you'll set up your conical flask with the bung in already and your magnesium in a crucible separated from the acid, so that you can shake the flask and the magnesium will come into contact with the acid, and we have discussed that in lessons before. So they wanted arranged equipment so the magnesium ribbon drops into the acid after the delivery tube is put in. And the other thing they wanted you to say was clean the magnesium ribbon, so sand that down. And again, I'm sure we have talked about removing that oxide layer before doing this question. That's what they wanted. Okay. Explain the difference in the melting temperatures of magnesium oxide and potassium bromide. There were some terrible answers to this. All they wanted you to say was comparing the ionic charges. You've got 2 plus 2 minus versus 1 plus 1 minus. Comparing the ionic radii. Magnesium and oxygen are small and therefore close together, whereas potassium and bromine are large and further apart. And therefore, and this was the mark that many people lost, comparing the energy required. So you need far more energy to separate higher charged, so the 2 plus 2 minus that were close together, high energy needed to separate those, whereas the 1 plus 1 minus further apart and lower charged, less energy needed. Okay, now this was really interesting, okay, and I strongly advise you to notice this. More award 0 overall if there is any mention whatsoever of London forces, any molecules, intermolecular forces, hydrogen bonding covalent molecule, any mention of any of those things, you get 0 automatically. Really harsh, but that was the 2019 paper. It does say ignore references to electronegative, and you had to be careful to talk about ionic radii rather than atomic radii. Explain why the electrical conductivity of solid potassium bromide is poor, but an aqueous solution of potassium bromide is a good electrical conductor. Anything to do with in solid, ions are in fixed positions, not free to move. It does conduct in solution because the ions are free to move. Okay, very straightforward, and actually I think easier than the mark schemes at GCSE I've seen recently. Deduce 2 possible reasons why the density of iron is much greater than the density of graphite. The first thing, and the most obvious thing that actually many people missed, iron atoms are heavier than carbon atoms. Iron, 56 grams per mole, carbon, 12 grams per mole. So even if you had the same number of atoms in the same space, iron would be 4.5 times as heavy. So the iron would be 4.5 times as dense. The other thing is that the iron atoms pack closer together than carbon atoms in graphite. Most people talked about, the fact that graphite was in layers, and any idea of more space between the layers in graphite was fine. But again, award 0 if there's any mention of iron molecules or graphite molecules. People did talk about intermolecular forces between the layers, I mean, I think you can just about get away with that, but really the layers are not molecules, so they're not intermolecular forces. This question is about chlorine and its compounds. That is an example of disproportionation. Why? Because the chlorine, which starts off as oxidation state 0, ends up in KCl as -1, and it ends up as KClO3 as +5. Okay, so it is both the same species being both reduced and oxidized. Disproportionation. Oh, there were some of you really struggle with this. Predict the shape and bond angle of the chlorate ion. Justify your answer. Okay, so here we can see that there's a double bond there, single bond there, and a lone pair. So around that chlorine you've got 1, 2, 3, 4 things. Lone pair, double bond to the oxygen, double bond to the oxygen, and a single bond to the O- there. So because of this, it's going to be based on tetrahedral, but you can't see the lone pair. So the shape of it will be like the bottom 3 bonds of tetrahedral. So it will be trigonal trigonal pyramidal. You've got to name it. You would predict a bond angle of 107 degrees, allow anything in the range 106.5 to 107.5. If you know the actual value, you're allowed to give it, but that's what it is. And you can annotate it on the diagram. And the reason for that is in a tetrahedral, the bond angles are 109.5 in something like methane, CH4, but because the lone pair is more repulsive than bonding pairs, that means that these angles are going to be closed up slightly, hence slightly smaller than 109.5. Why is it based on this? Well, you've just got to talk about 3 groups, or 3 lots of bonding electrons, and a lone pair. And discussing that the lone pair bond pair repulsion is greater than bond pair repulsion, and some indication that the various groups move themselves for minimum repulsion, maximum separation. I took it as implied, so that's what's going on there. Completing this equation, most people got this right, 4, 1, 3, balancing that. This was interesting. There were lots of people really struggle with this. Lots of people don't understand what these numbers mean. Solubility in water, 4.8 times 10 to the minus 1, 1.29 times 10 to the minus 2. That means this is far more soluble in water than this is. And lots of people getting that the wrong way round, not realising that minus 1 is bigger than minus 2. In fact, it's about 13 times more soluble in water. In ethanol, minus 4 and minus 6. Again, this is about... well, so if it was 8.7 times 10 to the minus 4, it would be 100 times more soluble. It's about a third of that. So it's about 30 times more soluble, again, in ethanol, potassium chloride. They wanted you to realise that actually they're both so insoluble in ethanol, there's no point using ethanol as the solvent. So the first mark was for realising that you just want to use water as the solvent. You basically add the products, so this stuff, add the products to water, and then you filter the undissolved potassium chlorate. So the potassium chloride should dissolve. The potassium chlorate, which is much less soluble, much less of it will dissolve. If you mentioned a separating funnel at all, you score 0. Again, a really nasty bit there. But if you thought you could do it with a separating funnel, allow salt for solid, etc. But they wanted you to say just dump them in water. Most of the potassium chloride will dissolve. Most of the potassium chlorate will not dissolve. So you filter the solution. Chlorine gas can be dissolved in swimming pool water to disinfect it. 2,500 meters cubed of water. Chlorine contents 2 ppm. Calculate the number of moles of chlorine dissolved in 1 × 10 to the 6. In the swimming pool. Okay, and you're even told, and I didn't know why they did this. 1 ppm is 1 gram of chlorine in 1 × 10 to the 6 grams of water. So you had to work out, firstly, the mass of water in centimeters cubed or grams. So you had to times that by 1,000,000. Okay, so that's the number of grams of water. You know that 2/1,000,000 of that is chlorine. So you take that number there and you times it by 2 and divide it by 1,000,000. So that's what they've done there. So that number is just a 2.5 × 10 to the 9. So times it by 2, divide by 1,000,000, and you get the number of grams of chlorine. Mass of chlorine, therefore, second mark. Divide it by the mass of a chlorine molecule to get 70.4 moles. Here, they weren't fussed about the number of significant figures. So 70.4, etc. was fine. Lots of people getting that there. And finally, when chlorine gas is dissolved in water, it reacts to form hydrochloric acid and hydrogen chlorate 1, or chloric 1 acid. The chloric 1 acid produces much more effective as a disinfectant than dissolved chlorine. Chloric acid is a weak acid and has little effect on the pH of the water. Right, loads of you still thinking high pH means more acidic. It doesn't. Remember, more acid, lower pH. That's year 8. Okay, so there's no excuse for you getting that wrong now. Use the equation. It's in bold. Use the equation to give 1 disadvantage of a chlorine content much lower than 1 ppm, 1 disadvantage of a chlorine content much higher than 3 ppm. So if it's too low, then you will have less chloric 1 acid and it won't work as a disinfectant. You had to talk about the right thing in order to get the second mark. Okay, so you had to say that would be lower, the chloric 1 acid, and so it wouldn't work as a disinfectant. But if you've got a concentration that's much higher than 3 ppm, you'll have too much HCl, and therefore you will get the effects of too much acid, so corrosive, irritant, etc. Okay, and again, you needed to correctly identify the hydrochloric acid as the problem in that case. Do not award higher pH. There you go. Lots of you doing that. Not a higher pH. Do not award increases acidity, toxicity, reasonable negative effect on swimmers, irritation. Ignore just harmful or dangerous. And ignore references on chlorine itself being the problem. Okay. But that was generally well done. I believe that the average marks was about 30 out of 48. Right, what you need to do now is go and do the rest of the 2019 paper 1, and as it says on Google Classroom, submit evidence of a couple of those questions to Google Classroom to show that you have done the work. Please do email me if you've got any questions about this. Your second lesson of the week will be looking at paper 2, walking through the mark scheme, and then your work will be to complete the rest of the questions from paper 2. Until then, have a nice week. Thank you.